Hello everyone and welcome to another video. Today I'd like to talk about writing systems of ordinary differential equations in state space format or as a state space representation. This is actually a very important topic because it forms the basis for a lot of the modern techniques of how to analyze higher order systems of differential equations and how those apply to a lot of different fields of science and engineering, more specifically things like control theory. So what we've talked about in the past when we were looking at ordinary differential equations is we showed how that you can use ordinary differential equations, or ODEs, to basically model a physical system or an engineering system or some system which has inputs and outputs, right? The whole idea with state space representations is we would like to take this system of ordinary differential equations and we just want to write this in a different format, namely in a matrix or vector format. So it's going to be the exact same system with the same inputs and the same outputs and the same relationship between the two. We're just going to represent them or write them down in a more compact, easily analyzable format. So that format, what it's going to look like is, in general, the nonlinear version of a state space representation of a set of ordinary differential equations basically looks like this. It looks like basically a vector system of first order coupled differential equations. So it looks something like this. The general form is you have x dot is equal to some nonlinear function of the states and the controls. That's what x and u are. And then the outputs of this system are, again, some nonlinear function. I guess we're calling it g here. That function is nonlinear in the states and controls. Okay, so again, this is a very generic, generalizable format. You can pretty much fit almost any system of ordinary differential equations into this general format. Again, there's a small asterisk on that. You can't fit every format. This is sometimes what's referred to as explicit form, where you're able to explicitly solve for the term x dot, okay? But we're going to go into some examples for that later. Let's just leave it like this. Now, let's talk about what are all of these things. What are x, u, y, f, g, all those things, right? So x is a n by 1, so it's a vertical column vector with n elements. This is what's referred to as the state vector. So this is incredibly important. As you can probably imagine, it's here in the name, right? State space representation. So the idea with this vector x is you are going to stack up in this vector x everything that you need to define the current state of the system. So if that's the position, the velocity, the temperature, maybe a combination of all those of your physical system, anything that is going to matter in describing your differential equations, the important variables are going to go in this state vector x. We're going to stack them up. And again, we're going to go through some examples of how we choose these and how you get this. But conceptually, this is sort of the most important vector of this entire representation is x. It's your state vector. And again, it's n elements long, okay? That's going to help dictate a lot of the dimensions of some of the other items, okay? Now, let's look at the other vector, u. U, this is what's sometimes referred to as your control or your input vector. So that's literally this guy over here. The inputs to your system are what we can call U. In fact, maybe we could even label this right here. You know, the inputs, the other way you can think about this is U is coming in here, right? So all of the inputs to the system, maybe that is, you know, throttle settings, gas pedal settings, volumetric flow rate of how much water you're dumping into this system, you know, whatever goes in as an external input to the system, you're going to stack these up into an M, right? M by 1 control vector. So again, these are these two very important vectors in here. As soon as you know the state and the control vector, you should be able to compute both x dot and y, okay? Let's talk about y here. So y, this is a p by 1. So again, it's another vertical vector. This is what's referred to as your output vector. So that's literally all the outputs to the system over here, y of t. What's coming out? So you have sensors to measure the altitude, the airspeed of your aircraft. Well, whatever you're measuring, you're going to stack all those up into this vector y, and again, you'll have p elements, okay? So these three vectors, the state, control, and the output vector, they pretty much help us define what this system looks like in terms of inputs, outputs, and what internal states matter for this system, okay? So with that being said, if we understand what x, u, and y are, we can start thinking about what are this f bar and g bar. So f bar, and again, I wrote the bar on top of it to denote that this is a vector, right? So this f bar, it's an n by 1 system of potentially nonlinear equations, right? So these are just going to be a vertical vector of potentially complicated vector functions. That's literally it, right? So again, you can see the dimensions n better match up with the dimensions of x, right? Because it's going to spit out x dot, right? So all this function does, all this f bar function does, you tell it the current state of the system, the current control inputs to the system. Its only job in life is to take those two inputs and compute what is x dot, right? How is the state vector changing with respect to time? That's its only job, right? Similarly, the g-bar function, it's also, again, it's another nonlinear function, but instead of computing x dot, it just computes the output. So this g-bar is sometimes referred to as, you know, like an output set of equations, where f-bar might be considered, sometimes you hear this set called a set of state equations or state transition equations, things like that. So that's what this looks like. Again, super generic, and unfortunately, it's a little abstract right now, but in just a second, we're gonna look at a concrete example of this, but I just wanna outline what the general format of this is. So again, all this is doing here is now we're talking about using this representation here for our state space input. So again, we have the exact same inputs u going in, the exact same outputs y coming out, but now in the state space representation, we are going to be maintaining the state vector x, and if we know what the state vector x of this system is, we should be able to understand how it's going to evolve over time under the influence of these control inputs u. That's the game plan, right? So again, this is a general nonlinear format of a state space representation. Now, if you luck out and you're able to get a linear state space representation, you could write this format in this format. So over here, this is a linear format. So it looks very similar where you have x dot is equal to something, but now instead of being a complicated nonlinear abstract function f bar, we can now write this as this very famous equation of x dot is equal to ax plus bu, and the output y is equal to cx plus du. So you can see this is a nice matrix and vector representation, I guess, of these functions, right? So here, this matrix A, you can, again, just see by dimensionality. A has got to be an n by n, and this is referred to sometimes as your state matrix, okay? B here has to be an n by m. It's called the control matrix. C here has to be P by N, and this is referred to as your output matrix. And finally, D has got to be a P by M, what's sometimes referred to as a feed-through matrix. So again, this is a linear format of a state space representation, okay? And we want to focus on this because actually the linear format is super duper nice, because if you have a linear state space system, a lot of tools come to bear that you can use to analyze this system in terms of its stability, its performance, and all these other tools become available. So in general, I think this is a good introduction to what is a state space format. So again, the takeaway here is what state space representation or state space format is talking about is starting with a system of differential equations. All we want to do is rewrite them in this form or this form, one of these two formats. I want to just rewrite them as a series of vector value of vector or matrix equations. And what's interesting about this is if you look at these two, I only see a single derivative. There's only x dot, right? I don't see x double dot, x triple dot, x 4 dot, anything like that. So it's a vector, a set of first order vector equations here. So what's nice about this is we're going to take a system of potentially higher order ordinary differential equations. We're going to write them into and reduce the order of it to basically a first order differential equation. That's the game plan, okay? So with that being said, I think what would be super helpful right now is let's look at an example of how we can take a real physical system and get it written down in this nonlinear state space format, and then we'll take an example of another physical system and see how that can be written as a linear state space format. So we want to look at how can I get state space representations out of two different systems. So give me a second to pause your camera, erase the board, and we'll go on to our first example over here of a nonlinear state space representation. All right, so I left the nonlinear representation up because that's the first example I want to look at. In fact, I want to look at this magnetic ball levitator that actually we talked about in our previous video where we were talking about our introduction to ordinary differential equations. In fact, the next two examples, this example and the immediately one following, are going to be looking at examples that I described in more detail in this video. So if you haven't watched our introduction to ordinary differential equations video, please take a moment, pause the video, go back, watch that one first, just so you can get a physical setting and where I describe these systems in a little bit more detail so you understand what they are and how they operate, and then come back here and we'll talk about how to model them as state space representations. So if you've already done that, again, here's that MBL system in operation. So again, maybe I'll flash up a video of it over there just showing how it works. Here's a very simple crude diagram of the system. It's super duper easy. It's basically a glorified mass spring damper system, right? I've got a mass, which is this ball. Let's label this, I guess, with mass M, right? And there's a spring. I guess the spring here in this case is this electromagnet, right? So the electromagnet is pulling on this guy with some spring, so let's call it F magnet. Right? There's some magnet force that is hopefully being applied appropriately to levitate the ball up or down, right? And then the output of this system is we are measuring the voltage that's output by this light sensor, right? So there's an LED over on the far side of the system that shines over and it's captured by this light sensor. So depending if the ball is too high or too low, it's going to occlude or block or shadow this light sensor by a different amount. Therefore, we can kind of get a measurement of where this ball is or get some idea of the height of the ball by measuring the voltage output of this light sensor, okay? So what I want to measure on this system is, let's talk about the position of the ball. So I'm going to measure the position, let's call that Z. So positive Z is the distance between the tip of the magnet to the center of the mass of the ball, measured positive downward, okay? So here's what the system looks like. Why don't we talk about how can we write this as a state space representation, okay? So the first thing that we need to do here is choose a state vector. Right, we talked about this earlier, that this state vector X was the most important thing about this system, okay? So I need to say, what do I need to know about this system in order to predict it or model its behavior? Well, since you know this is a silly mass spring damper system, you know that basically you need two pieces of information. You need the position and the velocity of the ball in order to understand what's going to happen. So what we're going to do is let's make this two things. Basically, I need the position of the ball, which is Z, and I need the velocity of the ball, Z dot. Those are my two states. So I basically have two states. Let's call them X1 and X2, right? Those are the two states of the system. So here's my state vector of the system, and we should be good to go with this, okay? The next thing I need to do is, let's talk about what are the inputs and the outputs to this system. So the inputs, right? So the input, what goes into this system? Well, the way this thing operates, or the way the external input to this is, I get to control the voltage that goes to this electromagnet, right? By increasing the voltage to the electromagnet, I increase the current, which increases a magnetic field, which pulls this ball up and down, right? So I basically am able to choose what voltage do I apply to this magnet, okay? So maybe let's call this, maybe I'm going to call this let's just label it like this, VM, for voltage to the magnet, okay? So the input to the system, I only have one input, a single input. Let's call this VM at any given time. I get to specify that, right? So here's my control input, or my control vector. It's just a single control vector of U1, which is the voltage to the electromagnet, right? Okay, so how about the outputs of this system? We can also do that very easily. So the output of this system is, I can measure the voltage from this light sensor, right? So let's call this, what did I end up calling this thing? I don't know. We can call this, I don't know, let's call it VS, maybe, for voltage from the sensor, right? So the output of this system is, again, I measure a single thing. I measure the output of this light sensor. So the only thing here is VS of T, right? So I have a single output. Okay. So at this point, I've got the state vector, control vector, and Y. And in fact, maybe I should have rewritten here what we're doing. We're choosing the state vector, control vector, and output. Right? That's easy to do. So at this point, we basically have to find the input, the output, and the internal state of this system. Okay? Now, where it gets interesting is, we need to now write down this equation F bar and G bar, right? Okay, so how do I get that? So the way I'm going to get that is basically from looking at Newton's, applying equations of motion to this system to describe how does this state vector change, okay? So let's go ahead and write a free body diagram on this ball, right? Maybe that's the easiest thing to do. Free body diagram of the mass. So I've got the mass here. Well, obviously you got what? You got gravity pulling down with magnitude mg, right? And then we've got a magnet force like we talked about. The magnet is pulling it back. And also this ball is sitting here in air or some viscous fluid. So there's probably some drag force on this. So I don't know, let's write it like F drag, something like that. Right? Okay, pretty darn simple system, wouldn't you agree? Why don't we leave it like that? So what I'm going to do is let's go ahead and apply equations of motion. Okay, so what are the equations of motion for this thing? Since the mass is constant, I think everyone would agree that a good set of equations of motion is Newton's second law. So this is what? Sum of the forces is equal to the mass times the acceleration, right? At any given time, something like that. Okay, so let's just start summing up all of these forces. So we got gravity, so we got mg, right, pulling down, minus F magnet, minus F drag, right, is equal to the mass times the acceleration. Let's think about this. Acceleration, isn't that just the second derivative of the position? So this is just z double dot of t. Would everyone agree this is the same thing? Okay? All right, so now what we need to do is we need to characterize these two things. What is the magnet force and what is the drag force, right? So let's come up over here maybe. Let's look at the magnet force. So how about magnet force? Fm, right? Now, this is where it gets a little bit interesting. So the magnet force, right? This is probably pretty complicated, right? Because what is this magnet force a function of? Well, if you think about this long enough, it's obviously a function of how much voltage you have on the magnet, right? That's going to depend on it. So F magnet is probably a function of the voltage. I meant the voltage. The voltage that you put across the magnet, right? It's also probably a function of how far the ball is away, right? Because as you know, the magnetic force from a given magnetic field, it doesn't fall off with, like, I don't know, 1 over r squared or distance squared. So the farther you are away from this magnet for any given voltage, the less force you're going to have, right? So if you bring the ball far, far away, you're going to feel the magnet force reduce quite quickly, right? And conversely, if you move it closer and closer, it's going to start getting harder and harder and harder, and it's going to start pulling it further and further in, right? So it's probably also a function of the position, right? And again, maybe I should have put sub t's on both of these because they can change at any given time, right? They're potentially complicated, right? So I need to write down some function, right? And here's where it gets really challenging, and here's where a lot of these nonlinearities come in. This function, or this mapping between how much force does the magnet apply to the ball given the voltage that you apply to the magnet and the position of the ball, this is an incredibly complicated function. In fact, I'll show you a screenshot. Here's some data that I collected in the lab for this particular system. And as you can see, this function is very, very complicated. So trying to fit this with some two-dimensional surface is going to have a lot of nonlinear terms, right? There's probably going to be a lot of, something like 1 over z squared or something like that is going to probably show up in there, but you're going to have weirdo things like, alpha vm. Again, I don't even want to try to fit this. So one other option here is we could also even say, you know what, just jam in that lookup table, right? This table that I'm showing over here of all of this experimental data, this doesn't even have to be a analytically describable function. We can leave it as a lookup table, right? So we could say that instead of having some function, how about just make this a lookup table of experimental data, right? So basically, you tell me the voltage you put on the magnet and the position of the ball away, and I'm just going to look up what is the magnet force via this mapping of experimental data that we've got here. So long story short, though, the thing to take away from this is that this magnet force is very, very complicated and very nonlinear, right? Okay, let's do a similar analysis. How about for the output? Okay, so sorry, I'm jumping the gun. The drag force, right? Let's do the drag force. So let me erase this real quick. We can easily do the drag. Well, not easily, but more easily. How about drag force? So we need to characterize F drag, right? Okay, so we can say F drag. Well, what is the drag on this cylinder or circular spherical object as it moves through the air, right? That's basically what we're looking at. Well, you know, a very popular model of drag is the coefficient of drag, right, times the dynamic pressure times some cross-sectional area, let's call this S, or some reference area S, times the sine of Z dot. Right? And in here, Q is sometimes, again, it's called the dynamic pressure, right? It's 1/2 the density of the fluid times the velocity, which is Z dot squared, right? So again, I don't think we need to dig super far down into this. Other than to say, again, look at this, non-linear, right? This function F drag, it's it's not as complicated as the magnet force, but it is clearly non-linear, right? You got a Z dot squared, you have this non-linear sine function, S-I-G-N, of Z dot. So again, it's non-linear. To make our lives easier, or relatively easier, you know, again, this is a modeling choice. We could say, you could either choose to model it like this, as complicated actual drag, or, well, again, it's not actual, right? Because it's impossible to get the actual drag, but this is a fairly accurate drag model. Let's make our lives a little bit easier. One other way you could do this is if we want to look at an approximation, or a bigger approximation, right? We could just say that the F drag, you know, you could use something like very simple viscous drag. You could say that the drag force is just some linear coefficient of drag B times the velocity, right? This is typically what you see in a linear spring mass damper system. Here's the damping term, right? It's just a linear coefficient B times Z dot. So we could use this. This might be more helpful because it's going to allow us to at least write the drag as being linear, okay? So, okay. Let's do that. Let's go ahead and come back to our equations of motion and see if we can massage this to get this function F bar, okay? So let me see. Maybe the easiest thing to do is let's erase some of this. And again, what we're trying to do right now is take our representations of all of these forces and basically get equations of motion out of this, okay? So how are we going to do this? So let's go ahead and write our expression for x dot, okay? So we said x dot of t, right? It's the time rate of change of the state. Well, isn't this just the same thing as ddt of x, right? Okay? Well, what was x? Right? If you remember, we said, okay, the state vector x, wasn't that the position of the ball and the velocity of the ball? Right? Wasn't that the same thing? This vector here is the same thing as a vector x, okay? All right, so let's just take the derivative of this, okay? So this becomes z dot and z double dot. Right? Okay, now look at this. If you remember, and unfortunately I think I erased, maybe what we should have done is I should have saved some of this, but anyway, you remember z dot, right, the velocity, isn't this the same thing as the second state, x2? That was the exact same thing, right? And furthermore, what is z double dot? Okay, and unfortunately I did just erase that, but if you remember from the equations of motion, didn't we say that sum of the forces is equal to the mass times z double dot? Right? So again, you could solve this for z double dot. So this is just F is equal to ma. I'm going to solve for a. So you could say z double dot of t, it's just what? All of the forces, what do we have? We have mg minus F magnet minus F drag, right? All this all over m, right? Wouldn't you agree this is the exact same thing? Right? Okay, so z double dot is basically what? It's g minus 1 over m times the F magnet minus 1 over m times F drag, right? Great, jam this into here. So this can go into here, down to the bottom, okay? So this just becomes x2 of t minus, down here in the second row, it's just g minus 1 over m times F magnet. Now, remember, we said this magnet force, this was this complicated lookup table, which was a function of the voltage on the magnet and the position of the ball, right? Something like this, minus the drag force. What did we say the drag force was? We said it was B times Z dot of T, right? This was our simplified model of drag. And then again, this is all over M, right? Because here's the 1 over M term, okay? Okay, so we're almost there. Now let's do one more thing, all right? So again, I will rewrite this. So the top stays the same. The first line is just x2 of t, right? This bottom one is g minus 1 over m F magnet. Okay, now the voltage on the magnet, what is this Vm? I guess I should have had a sub T there, right? Because this can change. Didn't we say this is just the first control U1 of T? Isn't that the first control input, right? We said we're able to change the voltage of this magnet, no problem, right? So this really can be rewritten as U1 of T, right? And then finally, what was Z? That's the position of the ball, right? Didn't we say earlier the position of the ball is just the first state, x1? So this is here, you can write this as x1 of T, right? Great, minus B over M Z dot. What is this Z dot term? Z dot is just the same thing as x2, right? So you can write this as x2 of T, right? There you go, right? And if you look at this, we basically have this entire thing. What does it equal? Well, it equals, this thing is just x dot of T. And now, if you look at this, the right-hand side is some nonlinear function of what goes into this, right? It's the states x1, x2, and the controls u1, right? That's the only thing you need in here. Of course, you need constants like g, m, and b. But this entire thing over here, this is effectively f bar, right, of x and u. Right? So we've basically achieved our goal here of we've written x dot is equal to f bar of x and u. So we finished this portion. We wrote down what is the state equations effectively in this nonlinear situation, right? Okay, so now, since we did that first part, let's talk about G bar. How are you going to get G bar? Okay, I should tell you what, give me a second to erase this and we'll tackle that next. All right, so now let's talk about the output of this system, right? Which we said was going to be the voltage coming out of this light sensor, right? That's the thing that we're measuring out of this system, okay? Now, what we need to do is, again, we need to come up with a function which will output this voltage given the state and the control input of the system, right? Given the state and the control input to this system, okay? So the way, again, that we're going to do this is we're going to get this experimentally. So again, I'll flash up a screenshot over here. This is showing a plot of what does this voltage output of the light sensor look like depending on the position of the ball. So again, this was calibrated in the lab where I moved the ball up and down to known positions and then measured the voltage output of the sensor. And as you can see, this clearly looks like another nonlinear function. That doesn't look like a line to me, right? So that's some nonlinear function that, again, we either need to use a lookup table or some analytical function to describe. Luckily for us, this function isn't so bad. In fact, it's quite nicely fit by using a sigmoidal type function. So in this case, I think what I used was a function, well, here, actually, I'll just write it up real quick, the function that I ended up using. I used a function that said Vs here was basically, it's only a function of the position, z of t. Right, and the way you get this is, I think the function that I used was just some constant a times basically I use a scaled sigmoid function, so 1 over 1 plus e to the minus alpha z minus z naught. Something like this here. And then in my case, I used an A of 5.1-ish, something like, again, this is just for illustrative purposes, alpha of about 1,000 and a Z naught value of, what did I use here? Oh, 0.025, something like that. Anyway, tell you what, I'll flash up a screenshot of what this function looks like if you jam in these constants, and you can see it's a pretty reasonable approximation. It gets you that nice sigmoidal shape, right, which seems to match with the experimental data. So again, this might be a reasonable model for the system, or for the output equation. And again, if you look at this thing long enough, you see that basically here, this thing, why don't I just call this G bar, right? Because that's what this thing does. You tell me the state or the position of the ball, I will tell you what the output is going to be, right? So you can see in this case why this output equation is really fairly simple. Well, I guess, again, fairly simple but nonlinear, right? So the output of this, again, it's just supposed to be the single voltage coming out of the sensor, right? This is just going to be the equation. It's a 1 by 1, right? But it's this basically, it's this A times 1 over 1 plus e to the minus alpha z of t minus z naught. And again, we could change this at z. Another name for z was just the first state, x1, right? Okay, so here you go. Here's your output equation. This is just the function g bar, where you tell it the state and the control input. Of course, there's no dependence on control input, right? I don't see U showing up anywhere, which again makes sense because the voltage output by the light sensor probably has nothing to do with the voltage I apply on the electromagnet. So you see U doesn't show up anywhere in here, but the position does. X1 shows up. So again, this is not too bad. And we're kind of done at this point, because now what we've done is we have fully characterized both the state equation, F bar, and the output equation, G bar. So now this state space representation, if I put this into here, right? This is basically now my MBL system, right? It's a nonlinear state space representation of this complicated nonlinear state space system, right? So there, I think that's a pretty good example of how to take, how this can kind of get complicated quickly if you're trying to model a real physical system, right? This was a very simple mass spring damper system, but we saw that the way we're going to model this is we are able to get it into this system of first order differential equations, but they're nonlinear. Okay, that being said, I think this is great. Why don't we look at an example now of a linear system? And again, I want to look at another example which we took a gander at when we were talking about introducing ordinary differential equations. So again, if you haven't had a chance to watch that Introduction to ODE videos, please make sure you watch that first, because we're going to come right back after I erase the board and look at an example of a linear system. All right, so now let's take a look at an example of a linear state space system. So here's the diagram again of this two-tank hydraulic system. Again, so just to refresh your memory, this is that same hydraulic system we were looking at in the Introduction to Ordinary Differential Equations video, where I built a little model of this, and we saw that the height of the two tanks of water depends on how much water you're putting in versus the initial condition of the two heights of the two tanks, etc., etc. And we said that this was the differential equations derived from fluid dynamics that basically describe how the height of the first tank, how its rate of change was a function of both its current height and the height of the other tank, as well as the volumetric flow rate in. And similarly, this was a differential equation which described how the rate of change of the height of the second tank depended on the height of the first tank and the height of the second tank, and all these other constants like the resistances of the pipes and the density and the cross-sectional area, all this stuff, right? Long story short, we took this system, we obtained two differential equations, right? And we said that these were two coupled differential equations, right? We saw that the equation for H1 dot, it involved obviously H1, but it also involves H2. And similarly, the equation for H2 dot, it involves H2, but it is coupled with H1 here, okay? So these are two explicit first order coupled differential equations. The question now becomes, how do I write this now as a state space representation, right? The idea is, again, what we want eventually is we want a system here, which is basically the state space representation of this two-tank hydraulic system, right? And the idea is something is coming in, right, which we called U. This was our input vector, and something was coming out of this, which we called y, which was the output. So the question is, what goes in this box in here? Well, it's these differential equations, but how do I write them in state space format? Okay, so tell you what, I think you'll agree that what we can do is, let's actually go ahead and rewrite these two equations in vector format. So in other words, what I want to do is I'm just going to write this thing as h1 dot of t and h2 dot of t. right, is equal to, well, it's equal to these two things, right? So, actually, you know what? If I look at this closely, I could write this like this. So I'm going to write this. Let me actually get a different color so I can kind of delineate. This is going to be a 2x2 matrix. I'll try, this green sort of shows up. Hopefully you can see that in the camera. Okay. So the green here, and then I'm going to factor out h1 of t and h2 of t like this. Okay. Okay, so now let's see, h1, the thing that multiplies h1 in the h1 dot equation here is this thing, negative rho g a1 over r1, right? So I gotta have in this first 1 entry, I gotta have minus rho g all over a1 r1, right? And the thing that multiplies h2 is this thing, positive rho g over a1 r1, right? So this is positive rho g over a1 r1. Right? And then, so I took care of this term and this term, so I need this term right over here. So I need to actually pull this QI, right? So again, this QI was the input to the system. It was the volumetric flow rate that we were putting in. So I'm going to write this over here, and let's see, I kind of didn't manage my whiteboard space very well. Let me scoot this diagram over a little bit. Okay, so we're going to have this thing y coming out over here. I'm just trying to shift everything over a little bit so we have a little bit more room. Okay, let's do it like this, okay? Okay, now back to our matrix equation over here. So then I need to add on this term of, also go ahead and use my little delineators here so we can see that this is a 2x1 matrix I'm making here. I'm going to pull out QI of t, like that, okay? Okay, so now I need to pick up this coefficient here, right? 1 over a1. 1 over a1. Okay, there. So I think everyone will agree this top row of this matrix equation is the exact same thing as this first differential equation, right? Similarly, let's do the same thing for this second differential equation, h2 dot. That's the second row of this matrix expression, right? Well, it is something multiplied by h1. That something is this coefficient right here. So I need to put in here rho g all over a2r1, right? And then I got this term right here. This is this entire ugly thing. Yikes. Okay, so this is minus rho g all over a2 times quantity 1 over r1 plus 1 over r2. There we go. Right? And then I need a big 0 down here because QI doesn't show up anywhere in this second equation. Right? Okay, so now if you look at this long enough, right, maybe, again, I'm not managing my space well. Let's put this U down here. This goes with a picture. If you look at this, what if we go ahead and choose now a state vector, choose or slash define, however you want to think about this. Let's choose the state vector x of t, right? Again, remember the state vector describes the state of the system at any given time. Well, the state of the system is defined by the height of the two tanks. Wouldn't you agree? H1 and H2. So I'll stack this up as this 2x1 vector. And what is the input to this system, the control input? Well, it's just this thing, right? The only control input is QI, right? Right? That's the only thing we have an external input to the system. So if you look at this long enough, what is this right here? This is basically x dot, right? Would everyone agree? This is x dot of t. This right here, here's our state vector x of t, right? And over here, this is our control vector u of t, right? Of course, a control vector is just a scalar in this case. And then this matrix right here, if you look at it long enough, it's just constants, right? The rho g, a1, r1, r2, all these are just numbers. This whole thing is just a constant number. Call this big matrix, call this thing A, right? This thing right here, this 2x1 matrix, call this thing a B, right? So if you look at this equation right here can be rewritten in our linear state space format of x dot of t is equal to a x of t plus b u of t. Right? Great, so this is half of our state space representation, right? This defines the dynamics of the states, okay? Now, we need to now define what are the outputs of the system, right? Because that's the second half of this diagram, right? So the outputs, let's go ahead and, here's where you get to pick. depending on what kind of sensors you have or what comes out of the system, let's say we have some way to directly measure H1 and some way to directly measure H2. So let's say we slap a sensor on top of this tank right here. You know, I don't know, maybe it's like some rod that we dip into the water, and this rod can measure this height. And same thing, we're going to dip this another rod into this other tank so we can measure H1 and H2. So what I'm saying is that the outputs of this system, remember, we are going to stack those all up in this vector y, all right? So we're going to have two outputs, like let's call it a y1 of t and a y2 of t, right? Two of these things. And what are these? We said, okay, that first sensor output is going to be H1 of the tank, right? The second sensor output could be H2 of the tank, right? So I need to write this now as a matrix expression of, I would like this to look like y equals cx plus du, right? I want it to look like something like a C matrix times x, right? What do we say was x? X is H1, H2, right? Plus a D matrix times U, and U in our case was just Qi, right? The volumetric flow rate in. So again, you see this is really interesting. This is a really simple expression. I need the first row of this to just basically say H1 equals H1, right? So in order to do that, I think you would agree I need to put a 1, 0, 0, something like that, right? The second line of this equation is going to be what? It's going to be 0, 1, 0, right? And then we have our expression of H1 equals H1, H2 equals H2. So great. Again, call this matrix here C, call this matrix here D. This vector right here is the state vector X. This vector right here is the control vector U. So again, we end up now with our final expression here of y of t is equal to cx of t plus du of t, right? So there we go. Here is our entire expression, the second half of the state space representation. So finally, we can fill in this block, right? This block, the state space representation of this entire coupled two-tank hydraulic system, is basically just our good old linear expression of x dot is equal to ax of t plus bu of t, right? And then the output y is equal to cx of t plus du of t, right? So this now is a matrix representation of these same two differential equations, right? So it's just a nice compact format. Just as a quick variation, you know, it doesn't, this C and D matrix was, the output equation was actually pretty darn trivial, right? We're basically saying we have direct measurements of all of our states. But, you know, what if you didn't have that? What if the only thing you had was, let's just say you only had the tank of H2. Maybe you didn't have this first sensor, right? You didn't have enough money to buy two sensors. You only had one sensor, okay? So all that means is that you just need to modify your C and your D matrix, right? So now we're saying we only have one sensor. That first sensor is actually measuring H2, right? Okay? And we no longer have this second sensor. So let me erase this, okay? So let's erase this second line. So we're not even going to have a second line, all right? Like that, okay? Actually, this C matrix should, I'll tell you what, let me do it like this. It's gonna be shorter, right? It's gonna only have one row because we only have one sensor, right? Okay? Something like this, right? Okay, so now all I need to do is just update the entries of my C and D matrix to reflect this new system. So now, right, the first output, the only sensor output I have is the height of the second tank. So I need to make this thing say what? 0, 1, 0. Would you agree? Because now this line reads H2 is equal to H2, which is kind of what we have. So now this is the C matrix and this is the D matrix for this reduced system where now you only have one output coming out of the system, right? So again, I think you'll see all the states, the linear state space system is nice because all you're basically doing is you're messing with the A, B, C, and D matrices, right? And that is completely going to define your system of differential equations. The other thing that maybe I want to come back to and maybe mention as a parting shot here is the linear state space system is really nice because it also helps you understand some of the coupling between these systems. Remember, we talked at the beginning that these two systems, tank 1 and tank 2, are coupled together, right? The height, the rate of change of height, the water height in tank 1 depends on not only its own height but also its of tank 2, right? These two things, they interact with each other, right? And you can see that interaction a little bit in this A matrix, right? Because if you think about it long enough, this A matrix kind of captures some of that coupling, so to speak, because you see it's fully populated, right? There are entries everywhere, right? So we see that this top row, right, relates to H1 dot. So this first entry here, the A11 term, you can kind of think of it as how does the tank 1's own state influence itself, right? Because this term, right, talks about how is H1 dot influenced by H1, right? This A12 term here, this is talking about how is H1 dot influenced by H2, right? Because you see that's how they get multiplied. So these off diagonal terms here and here, right, are sort of measuring this coupling between the two states. If one of these terms turned out to be 0, like for example, let's just pretend this was 0. If this entry was 0, what this is basically telling you here is if you look at the structure of the A matrix, you'll see that, okay, tank 1 is coupled with tank 2, right? Because this off diagonal is non-zero. But tank 2 doesn't give a hoot what tank 1 is doing, right? Because there's a big fat 0 here. It doesn't matter what the height of tank 1 is. It will not influence tank 2. So that might be like, I don't know if you had some like one-way valve, or I don't know how you would cook this up, but I'm just saying from the A matrix you can learn quite a bit about your system, right? You can learn about how the internal states are coupled, right? So again, let me put this back to where it was. I think what it was, this was rho G all over A2 R1. Okay, and furthermore, the B matrix is also kind of interesting. It's another thing that you can look at. It kind of helps you understand how does a given control input influence a specific set of states. So you see right here, what it says is QI, the volumetric flow rate, it actually only directly influences H1 dot, right? Because you can see the top row of this B matrix is non-zero, and the second row is exactly identically equal to 0. So what this is telling you is whatever you do, no matter how much you dump into the first tank, you only directly influence H1 dot. It doesn't directly influence H2 dot. Now, I use that term, that adverb directly, because it's very important here, right? Because we saw that these two are coupled. So tank 1 does indirectly influence tank 2, just not directly through the control input U. So again, this is a little bit of a tangent here, but I thought it's important to discuss it because I think the A, B, C, and the D matrices, again, they tell you everything you need to know about the system, and we're going to look into that a little bit later as well. But again, this is just an example of how you can take a set of differential equations, write them in vector format, matrix format, and you can basically obtain a linear state space representation of that system. All right, great. So now what I would like to do is I would like to look at a procedure of how we can basically take any nth order ordinary differential equations, you know, 4th, 5th, 6th order differential equation, and reduce it into a state space representation, or rewrite it into a state space representation. So the general procedure of how to do this is step 1 is you're going to take that ODE and you're going to solve for the highest derivative. So in other words, you know, it's an nth order ODE, so there has to be some term in here of basically dz to the nth derivative, right? So this is the nth order derivative of the independent signal, right? So this is what you want to do. You solve it for this term, okay? Once you've done that, step 2 is you're going to go ahead and define the state vector as the independent variable first derivative, second derivative, yada yada, all the way up to n-1 derivatives, right? So you're gonna stop at n-1. So this gives you a state vector of length n, right? So it's an n element state vector, okay? Then once you do that, step 3 is you're going to define the control vector as, again, just stack up all of the different independent inputs or external inputs to this system, or the control inputs, stack them up. There should be m of them, right? You put those all up in the control vector. And then once you have those two defined, it's step 4 is you basically just write the state equation down. So if it's nonlinear, you're going to have to keep it in this form that we talked about earlier. If it's linear, you'll be able to reduce it down to this ax plus bu, right? Then, once you've done that, you can go ahead and write the output equation, which again, here's the nonlinear form and the linear format. So that's the procedure. Let's go through an example of how this might work. So let's look here at this example here. This here is, if you stare at it long enough, this is actually a 4th order, and it's actually a linear ODE, okay? So what I want to be able to do is take this 4th order differential equation, right? Again, it's 4th order because you see z 4 dot, right? The 4th derivative of z minus 3 times the 3rd derivative of z plus 2 times the 2nd derivative of z plus 6 times the 1st derivative of z plus 4 times the signal itself has got to equal 3p plus 5q. So again, p and q are external inputs to this system. So the question is, you've got this 4th order differential equation. How do I turn this into a system of 1st order differential equations? In other words, how do I turn this into a states-based representation which has 4 states into it, right? Okay, so let's just walk through our procedure, okay? So step 1, and in fact, what I want to do is I want to solve for this here. So actually, I know you probably can't do this on your notes, so you might hate me for doing this, but step 1 is solve for this. So move all this other junk to the other side of the equal sign. So I tell you what, let me do this. Let me just move the move the equal. So I'm going to say this equals 3, and then I got to switch the sign, minus. I think that's the same thing, right? So I moved it all to one side. I basically have solved for z4 dot, right? That's the first step, right? Solve for the highest order, okay? So box this up. We're going to come back to him in a second, right? So here is z4 dot, okay? So now, step 2. Right? Step 2 is define the state vector. So in this case, we have x of t is going to be, in this case, we're going to stack all these up. So I'm going to take the first, the signal itself, then I'm going to go to z dot, then z double dot, and then finally z triple dot, right? So I stop at n minus 1, right? So I stop at, in our case, n is equal to 4, so I stop at 3 dots, right? So here is my 4 states. So here's x1, x2, x3, and x4. So again, the way to think about this is the first state is just the signal, the second state is the signal dot, third state is the signal double dot, fourth state is the signal triple dot, right? Okay, so we've got that. Actually, over here we can probably do step 3. Step 3 is also pretty easy, right? Step 3 is just define the control vector, right? So we need to take all of the independent or external inputs and stack them together. So in this case, there's only 2 of them, right? So there's p and q. So why don't we just do p as the first one, q as the second one. The order is arbitrary as long as you are consistent. You can do it in any order. You could have done q and then p if you wanted to, but again, just make sure you know which one are you calling the first state, which are the first input, and which one you're calling the second input. So in this case, I've done it in this order. Okay? All right. So there. Okay. So now, step 4. Is we are basically going to just write the state equation. So I know I'm in this linear case, so I'd like to get it to look something like this. So let's see how can we massage this. So again, let's just write down what is x dot, right? This is just the time rate of change, or the ddt of the state vector, right? Wouldn't you agree this is the same thing as ddt of what is the state vector? It's this thing right here, right? It's z dot, z double dot, z triple dot. Right, would you agree? Okay, so now if I just take the dot, I just need to add 1 dot to each one of these signals, right? So this is now z dot, z double dot, z triple dot, and z quadruple dot, right? Okay, now this is where it gets really interesting. Let me start down here on the next line so we have a little bit more space. What is z dot? Okay, z dot, if you look right here, z dot is the same thing as the second state. So I can basically write x2 here, right? How about this one, the second thing, z double dot. Z double dot is the third state, so this is x3. Similarly, z triple dot right here is x4. So this is x4. And now here's z quadruple dot, and this is why we solve for it up here in step 1, right? So z quadruple dot is this thing up here. So I'm just going to take the right-hand side and put it down here in this bottom row. So if I stare at that correctly, this is 3z triple dot, right? Again, what is z triple dot? Z triple dot is just x4. So I can write this as 3 times x4, right, minus 2 times x double dot. What is that? X double dot is here, x3, right? x3 minus 6 times z dot. Again, z dot is just x2, right? So this is x2 minus 4 times z, and z here is just the first state, so this is x1, right? Plus 3 times p. What is p? P is the first control input, right? So this is 3 times u1 plus 5u2, right? Would you agree this is the exact same thing? Right? Again, let me make sure I got all the signs of this correct. 3x4, negative, negative, negative. Yeah, okay, good, good. Right, okay, perfect. Now, if you look at this, I can write this as in a matrix format. In fact, let me come back. Shoot, I didn't manage my space very well. Let's do this over here. Right, so again, the left-hand side of this thing is x dot, right, is equal to, I want to write this whole thing in matrix format. Okay, so I'm going to write this as a big 4x4 matrix times x1, x2, x3, x4, right? This plus, this is going to be a 4x2. Yikes, see, I ran out of room. Shoot, okay, tell you what, let me erase some of this so we get a little bit more space so we don't have to be so cramped. I'm going to erase this. Times u1, u2. Okay, and again, let me maybe delineate the dimensions of this. So this is going to be a 4x4. And this one is going to be a 4x2, something like that. Right? So I just got to make this, I got to make this equal to this, right? So the first row of this expression has just got to equal x2. So I got to have a 0, 1, 0, 0, 0, 0. Would everyone agree that this top row just reads x2? Similarly, the second row has to just read x3. So I need a 0, 0, 1, 0, 0, 0, right? The third row has got to just read x4, so it's going to be 0, 0, 0, 1, 0, 0. And now all the magic happens in the bottom row of this. So the bottom row is this kind of, I needed to read this complicated expression. So this term right here picks up the x1, so this has to be the negative 4, right? So this has to be negative 4, negative 6, negative 2, positive 3, and then what picks up the u1 and u2? So there's a 3 in front of the u1, so this has to be a 3, and then what picks up the u2? This is a 5. Right? Would everyone agree this is the same thing? Right? So perfect. If you look at this, I got x dot is equal to some matrix times x plus some matrix times u. So this is your A matrix, and this here is your B matrix. So here we go. We've basically done this step, right? We wrote this thing down. We started with this, again, fourth order differential equation. We now have reduced it into an x dot is equal to ax plus bu. So we turned it into a set of 4 first order coupled differential equations. So this is pretty darn powerful, right? This is pretty exciting, okay? Now, just for completeness, let's go and do step 5, okay? So step 5 is I need to write the output equation. So let's do this over here maybe. I'll get a little bit more room. And I don't think we need, no, let's leave this definition up, okay? So step 5 is getting the output equation. So here you have to ask yourselves, what are the outputs of this system? And I guess we can be a little bit, I don't want to say arbitrary, but let's make something up just for practice. Let's say there are 3 outputs, like a y1, a y2, and a y3. Okay, so let's say that you've got these weirdo outputs. How about the first output is you buy a sensor which measures, I don't know, like, or you know what this z is, right? So let's make the first output just the signal itself. right? Or the independent signal, or the independent variable z. Sorry, I think I was saying the dependent variable z. The independent variable is time. The dependent variable is z. Okay, so let's just say that's the first output is the z. Okay, let's say the second output of the system, I don't know, something funky. Like how about z double dot plus 3z triple dot. Who knows? Make something up, right? And the third output of this, let's say it's 4 times q. Again, who knows what the output of your system is? Like maybe this is what your model is. Okay. So again, all I need to do now in step 5 is take these outputs and write them in linear format, right? Write them as cx plus du. Okay, well that's not that bad then, right? So all I have to do is I have to write this thing as it's going to be a matrix. Something times x, right, which is x1, x2, x3, x4, right, plus something times u, right? U was u1 and u2. Okay, so again, there are 3 outputs. So again, just from a dimensionality perspective, maybe what we should do is we should hash this thing out. So we know that this matrix has to have 3 rows. And then since it's going to be multiplied by a 4 by 1 vector, that has to have 4 columns. So let's write this like this, right? Similarly, this matrix has got to have something like this. It's got to have 3 rows and 2 columns, right? Okay. So again, I need this first row, right? The first output is just z. Well, z is just x1, right? So this first row, I could have just called this thing, this is the same thing as calling this x1, right? Right? So this is just 1, 0, 0, 0, 0, 0, right? Similarly, this second output, right? It's z double dot plus 3z triple dot. Well, what is z double dot? Z double dot is just x3, right? So I could just call this, I could change this, call this thing x3. Similarly, z triple dot is just x4, so another name for this is just x4. Right? So the second line better read x3 plus 3 times x4. So I need this to be like a 0, 0, 1, 3, 0, 0, right? Does that make sense? And finally, this last line, it's 4 times q. Well, what is q? Q is just u2. So another name for q is I could just replace this and call this u2, right? So the second line just has to be 0, 0, 0, 0, 0, 4. There you go, right? And now what we have is we have written this thing as y equals some matrix. Let's call this thing C. Y equals cx plus du, right? So isn't this fascinating? This is pretty darn cool. We took this system right here, right, which was the original 4th order differential equation. And again, just to refresh your memory, maybe what we should do, maybe I'm gonna, you might hate me for doing this, but I'm gonna try to do some horrible board art real quick, right? Conceptually, this differential equation, this 4th order differential equation, it has inputs, right, of u as being these 2 things, right, p and q. Right? You input P and Q. I don't know what P and Q are. Maybe P is the elevator, Q is the rudder, or something like that. Those are the inputs to the system. The system responds or is governed by this differential equation, and coming out the other end, oh shucks, I ran out of room. Darn it. How about like this? Why? Sorry, that's kind of ugly, right? Why are these 3 outputs? Maybe it's the altitude, the airspeed, and the pitch rate of the aircraft. You know, maybe if this is an aircraft model or something like that, right? So you've got these inputs, you've got these outputs. It's governed by this differential equation. We just showed how you can now write this in an equivalent state space representation. So this thing could alternatively be written as, again, same inputs. U is coming in. It's elevator and rudder. Sorry, I can't remember which ones we called them earlier. But then you've got these outputs, right? Which was these 3 things, y1, y2, y3. Again, who knows what they actually represent. But now, internally, the way we're going to simulate or solve this system is instead of representing it as a 4th order linear ordinary differential equation, we can write this thing as basically x dot is equal to ax plus bu, y is equal to cx plus du. Right? So here is the state space representation, And I would make the argument that this is actually a much nicer, more compact, easily analyzable system. And in fact, we're going to be able to learn a lot more information from this state space representation than we will be able to from this ordinary differential equation. Again, the two are mathematically identical, right? This is just a more convenient, compact way to write this. And in fact, what might be helpful or an interesting side study is let's run over to MATLAB Simulink, and we know how to implement and solve arbitrary order differential equations by building them up using individual integrators and gains and summation blocks and all that stuff. I want to show you that you could also do this all in one shebang using a single block in MATLAB, in Simulink, which is this state space representation. So tell you what, let's do that right now. Let's jump over to MATLAB Simulink and talk about implementing this block versus this block, simulating the two and seeing if there's any differences. Alright, so here we are in MATLAB. Actually, this is surprisingly simple. All we're going to do is just define the A, B, C, and D matrices just like we did up on the board. And then maybe the only thing that's kind of interesting is for our state space representation, remember, we also have to define an initial condition. So in this case, since our state vector is actually a 4x1 column vector, right? So now what I'm doing is I'm defining an initial state vector, which I'm going to call x0. So again, I'm just going to make up some numbers, 1, 2, -3, pi, you know. And again, keep in mind, right, the way that we ordered the state vector was the first state was actually z, the second state was z dot, the third state was z double dot, the fourth state was z triple dot. So therefore, these initial conditions, this is actually the initial z value of 1. The initial velocity of this should be 2, etc., right? So just again, keep in mind that now with our state space representation, we still have 4 initial conditions, but they are all stacked up together into a single vector, right? Okay, so with that in mind, what we can do now is we can go ahead and build ourselves a Simulink model. Well, actually, tell you what, let me first run this script so that we can initialize all those variables. And now let me come over here and I'll show you the Simulink model that I built. So in this case, I have 2 inputs, just like we talked about earlier, P and Q. These are the 2 inputs. I'm using a sine wave and a repeating square wave as these 2 just representative signals. So now let's take a look at this first model up here. This is the traditional way, or the way that we used to build Simulink models, right? If I look under the hood and double click this, you see that it's basically a system of integrators, gains, summing blocks. We've talked about this before, right? We talked about this in how to build Simulink models to solve ordinary differential equations, and that's exactly what we're doing right here, right? I just line up these 4 integrators, and as you can see, these integrators, if I double click on them, I am pulling the appropriate initial condition off. So this integrator here is going to be z0, and then this is going to be z dot 0, so I get the second element of that initial condition vector, etc., right? So all of this is basically numerically solving that system of differential equations. In fact, sorry, not a system, it's solving that 4th order differential equation that we started off with, right? So this is sort of the, let's call it the quote-unquote naive way, or I guess the way that we used to do it, maybe the old school way of solving differential equations. You can see that it's a little bit of work. You have to cobble together all of these blocks, hook them up, route all the wires, yada, 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 right? It should work, though. Now, let's compare that with my second model down here. This subsystem, if I double-click here, look at this. MATLAB Simulink has a single block called the state space block. And again, the way you get to this is you come here to your Simulink browser, you come here to continuous, and you'll see that there's this block state space. So I literally grab, dragged, and dropped that into my model. And if you double-click on this, you can see all you do is you tell it the A, B, C, D matrix, and you tell it the initial condition, just like we did earlier in the MATLAB script. So I already defined all these variables. So this is basically, should hopefully be equivalent to this upper block. Hopefully these 2 things do the exact same thing because they're solving the same differential equation, right? But again, just compare the differences. Look at this one. This is the old school way, right, of how to solve that 4th order differential equation numerically. And now here's how to solve that 4th order differential equation by writing it as a system of 4 first order coupled matrix differential equations, or basically writing it as a state space representation. These 2 things should hopefully do the exact same thing. So that's what I'm doing here in this block over here. I'm comparing the results. I'm comparing the Y that's generated by the traditional method versus the Y that's generated by the state space method. And if I come in here and you take a look, I apologize for a bit of the spaghetti. It's kind of ugly, but all I'm doing is, as you know, there were 3 outputs, a Y1, a Y2, and a Y3. So I'm just comparing Y1 that was generated by the traditional, what I'm calling the ODE method, versus the Y1 generated by the state space method, and et cetera for Y2 and Y3. So if I open up this scope, and if I go and hit run on this model and drag this over, look at that. It's beautiful. These two things are right on top of each other. So again, we see that basically these two models are numerically equivalent. I sure prefer this one though, because doesn't this look a lot nicer and a lot cleaner than the mess of spaghetti and wires that are hidden in the ODE model. So with that being said, I think this is probably a good spot to leave it, right? We discussed how to take a differential equation, either a nonlinear or a linear differential equation, and turn that into a state space representation, or just simply write it in state space format, right? All that is talking about with state space is literally just rewriting the differential equations. Instead of having an nth order differential equation, you're going to write this as a system of coupled first order differential equations. That's literally all state space representation really is. But now that we have it written in state space representation, a lot of tools come to bear that we can use to solve these things or analyze their performance, their stability, all this kind of other good stuff. So, in fact, that's the discussion of our next video, when we're going to start investigating how would I analytically solve for the solution of this state space system, right? Here in Simulink, by definition, we're doing this numerically, right? We have no idea of the underlying behavior of the system because we didn't do any analytical analysis yet. So that's what I would like to look at in our next video, and I hope you'll join me there. So I hope you enjoyed the video today, and if so, I also hope you'll consider subscribing, leaving a comment, hitting the like button. Any of those things help me continue making these videos, and I'd really like to get your input. That being said, also remember that the new videos come out every Monday, so I hope we'll be able to join you and see you at one of these future videos where we can all learn something new together. So until we talk again, I think I'm going to sign off. Talk to you later. Bye.